good afternoon, good morning, good evening, whenever you happen to be watching this video, and welcome to part 1 of lecture 5 of ENGR 2301 Engineering Statics. So, like I've mentioned, this is part 1 of the 5th lecture in the video series, and today we are going to begin our discussion of moments. So let's first look at moments and do a bit of a review where we've been and where we are going. So, I think in this first part of the lecture, it's going to be a relatively short one. We're just going to go over a brief discussion of what a moment is. In case you're not familiar with it, or you haven't heard the term before, or if it's been a while since you've had your physics courses. So, a moment, or moments, are a tendency for an object to rotate. That is perhaps the simplest way of describing what a moment is. So, everything that we've looked at up to this point in the course has been point particles. So, if we have a point particle, we described how there were a variety of forces applied to it, and we asked how, if this is a dynamics class, we would ask how does it move. But in statics, we were asking, okay, what is the relationship between these forces? What do the forces have to be? What do the angles have to be? What can we say about the system in order to keep the thing stationary or in equilibrium? So that's point particles, and that's what we've looked at so far. And we remember that the important thing about point particles is that they cannot experience rotation because, as we saw in some of our earlier lectures, because there is no dimension on a point particle, it has no moment arm, it has no tendency to rotate. So now we're moving on to rigid bodies. And these are things that have dimensions. So if you have a generic rigid body, and if it has a center of mass at some location, well, if we go and apply a force to it, that is going to do two things. So if I go and apply a force to this, here, and it has a certain line of action here, this is going to do two things to this object. Assuming it's moving in free space or just floating in space or something, if this object were floating in space or otherwise unconstrained, this would have a tendency to move in this direction and a tendency to rotate about the center of mass like there. Now, that would be more of a dynamics problem, but in statics cases or in statics problems, you still have the tendency to rotate, but that tendency is going to be resisted by other forces. And so, again, a moment is a tendency for an object to rotate. So let's talk a bit more about this. First of all, I'd like to introduce the idea of the principle of transmissibility. And we may have discussed this before a bit, but I would like to spell it out here. Just a bit of theory that's useful when talking about moments, and we will use this. Now, you can use this when doing force balance, but you use it most often when doing moment balance. So if you have a rigid body with its center of mass at some location, and if we draw that force again, applied somewhere to the body, and then it has a line of action here. What I can do if I wish, if it's useful, when I say what I can do, I'm talking about more in terms of analysis and conceptualization and math and such. A force, if this is a force F can be moved anywhere along its line of action. Anywhere along its line of action. A line of action. And it will produce the same rotational and translational tendencies as before. And its rotational and translational tendencies will not change. Tendencies / effects will not change. I guess that should be an E, effects. So in other words, as I have this drawn, I have this basically coming here and okay, for example, let's say I have a great big block or just a simple piece of material. Now I have a certain, so maybe its center of mass would be right at its middle. It's maybe I think just like a big uniform wooden block or something. If I come along and push it with a force of say 10 newtons, it's going to have a tendency to move and a tendency to rotate. But I can move that anywhere along its line of action. And so what I mean by that is, imagine instead of pushing at that location with a force of 10 newtons, what if on the opposite end here, right here, again, in line with its line of action, I were to instead pull with 10 newtons. So maybe I attach a rope to it and I pull with a force of 10 newtons. It wouldn't matter if I was pushing on this end or pulling on this end with a force of 10 newtons. It would have the exact same tendency to move the object and rotate the object. And it also doesn't matter the length of that rope. Like I could have a tiny little rope that's, a couple centimeters long or a couple inches long, or I could have a rope that's, 100 feet long or 100 meters long. Well, as long as the rope isn't sagging and things like that, that's going to start run into interesting issues. Or the same thing here. It doesn't matter if I have my hand placed against this or if I'm like poking it with a really long pole or something like that. It doesn't matter. As long as the force vector is the same, the direction of the force is the same, and the magnitude of the force is the same, I can apply that anywhere along that force's line of action and it will not change the effect of it. And where this will be very useful is when doing moment balance, especially when we're doing the scalar form moment balance, which we will see in the second part of this lecture. So, components of a moment. Let's talk about what you need to have a moment. And maybe I shouldn't say components because that sort of implies a Cartesian components. I don't really want to. That's not really what I'm trying to get at here. So let's talk about parts of a moment. What goes into making a moment? And fundamentally, a moment is made of two things. In order to have a rotation, you need two things. One, you need a moment arm. Moment or lever arm. And two, you need a force perpendicular to that moment or lever arm. Lever arm. Don't know why I wrote my L there, almost in cursive. Lever arm, there. Okay, so let's talk about let's talk about or describe some situations where you would not have a moment. So let's say I'm talking about generating a moment about force or about point P. Let's see. I wish to generate a moment about point P. About point P. So I'm going to describe three situations here. And these are just three independent situations, and talk about how each one of them would or not produce a moment. So let's say I have a force that's just going right through P. If I have a force directed right into P, there will be no moment. No moment will be generated because the force's line of action passes right through the point. Force's line of action passes right through the point. Passes through P, therefore no moment produced. So therefore no moment produced. Okay, so let's say I have something else. Let's say I did have a lever arm, or at least I thought I did. So I have some lever arm, and then I apply a force like there, somehow. So I apply a force F here. I have a lever arm, well at least I have some distance. It's not really a true lever arm though. But really this is just another case of the first condition. There's no component that is there's no component of this force that is perpendicular to the lever arm. So no perpendicular component of force. Therefore, no moment. And really, if you think about this, This is just the same case as this, because again, we like I mentioned, we can move a force anywhere along its line of action, and applying the force directly on it or at a distance away doesn't really matter. If it's pointing directly at the thing, it's still directly at the point. It doesn't really matter. Okay, so what would a proper lever arm force setup look like? So let's go ahead and do this little orange lever arm. And I am going to illustrate that the force doesn't actually have to be perpendicular. It's just that some component of it has to be perpendicular. So I am drawing this, so I'm deliberately drawing this. This is not just my poor art skills, which are admittedly an issue in this course, but I am drawing this so that part of it, so one component of this will be parallel to the lever arm and one component will be perpendicular. But this will still generate a moment. And the reason for that is at least some part of this force is perpendicular to the lever arm. So some part of F, or some portion of F, is perpendicular to the lever arm, and therefore a moment is produced. So when I'm teaching statics in a physical classroom, one of my favorite demonstrations to do is when and it always it illustrates the idea very well, and also it gets a lot of attention and wakes people up, because it's basically what I love to do is use something that's in every classroom. It's a door, and I love to go to a door or go to the classroom door and just basically make a fool of myself trying to open the door the wrong way. It's like I don't know how to use a door or something. So what I'll do is, have a classroom door, and this would be looking down on it from above. So this would be like, imagine a bird's eye view of a door. And what I'll do is I'll go up to that door, and let's say the hinge for the door is here. I'll basically illustrate all sorts of ways that you shouldn't try to open a door, and then I'll get a faux exasperated, like, man, this is so hard, I can't figure this out, why doesn't this work? And I'll ask the class, okay, why doesn't this work? And they'll explain that doesn't work because of the reasons we talked previously. So the first stupid thing I'll do is to try to open the door by pushing right on the hinge, and that doesn't work. Now, opening a door is a dynamics problem. It's a dynamics problem versus a statics problem. It's actually moving, but the principles are the same. And in order to open a door, what you need to do is you need to overcome the frictional force in the hinge. And normally, when you apply it, when you open a door the correct way, or at least anything reasonably sane, it doesn't really take that much force to open a door. Any kind of reasonable use. Well, I guess my cat can't open a door, but depending. So if I, when you apply a force to a door, like on its handle, which would be over here, maybe I can actually sort of draw that even. The door's handle would be here or here. When you apply a force here, you have a large moment that you're generating, and that is where that force goes is to both move the door, but the minimum amount of force required, there is still a minimum amount of force required. So it's not like you can apply a very, very, very tiny force and then just have the door slowly accelerate. There is going to be a minimum amount of force needed to open the door, and that comes from the internal friction in the hinge. So if you had a perfectly smooth hinge, an ideal, perfectly balanced, perfectly smooth, frictionless hinge, you could come along with, the force of a feather, a force equal to the weight of a feather, and just, you could open the door by blowing on it with your breath or something, and just sort of slowly open it, and it would just slowly move. But that doesn't work in real life, and the reason is because at the very minimum, you can open a door slowly, but at the very minimum, you have to apply enough force to produce sufficient moment to overcome the internal friction in the hinge. So if I try pushing directly on the hinge, well, I'm definitely using enough force, but I'm applying it in a very poor location. So I don't have a moment arm, so the door doesn't open. And this is a lot funnier when I'm doing it in a classroom, because I'm just sitting there huffing and puffing and, leaning against the door hinge with all my weight, trying to open the stupid door up, and it just getting exasperated and making a big show of it. It's like, why won't you open? And it's lots of fun. But anyway, that's one stupid way to open a door. And another stupid way to open a door, or try to, is I will do it so that basically as close as I can. I'll put my hands up against the door and basically try to push either away or towards. Basically, almost all of my force is directed along the axis of the door, along the length of the door. And so that illustrates this case here, where almost all of my force is going, very little of my force is perpendicular, and so little of that force is perpendicular to the lever arm, the door's axis of rotation, or sorry, that so little is perpendicular to this lever arm that it doesn't have enough internal force to move. And then, of course, I just go and oh, that wasn't that bad, and I just push on the door and it opens easily. So, again, this will not open the door because the line of action passes directly through here. This will not open the door because there is no perpendicular component, and this will because it has both. And really, that's the basic idea of moments. In order to have a moment, we need a certain distance, and we need a force. When we combine a force and a distance, then we will produce our moment. And fundamentally, that's what a moment is. It represents the tendency of an object to rotate, and that tendency to rotate is produced by both a distance and a force. And if you have both of those, you'll create a tendency to rotate, and your object, if it's free to move, will rotate, or otherwise it will be constrained, and you'll be able to calculate those constraining forces. All right, that'll do it for part 1. I just wanted this to be a brief introduction to moments. In part 2, we'll start looking at the mathematics of this, looking at moments in their scalar form. All right, that'll do it for now. Thank you for watching. I'll see you soon in part 2. And as always, thank you.